Good morning. Our second lecture presentation on thermochemistry is going to be focusing on Hess's law and the different ways that we can calculate enthalpy changes for either a physical process or a chemical reaction. So we have 5 different ways that we can calculate enthalpy changes. This video is going to cover 4 of them. So we'll start off with looking at stoichiometry, standard heats of formation, Hess's law of summation, and bond energies. The 5th way, when we can look at Gibbs free energy, will be covered in our next lecture video. All right, so let's get to it. When we are looking at our first problem here, we have the complete combustion of ethanol, C2H5OH, molar mass 46 grams per mole, proceeds as follows. C2H5OH plus 3O2 forms 2CO2 plus 3H2O, and it tells us the delta H for the reaction is negative 555 kilojoules. So when you're looking at any of these different reactions, you can treat the heat as if it is a reactant or a product. Remember, if I have a negative delta H value, then that means that the process is exothermic, and so I could list the heat out to the side. So you can kind of think about it as being part of the mole ratio. If I had a delta H as a positive value, then it would form as a reactant. So you can use that as a molar ratio there. So when we look at this problem, what is the enthalpy change for the combustion of 15 grams of ethanol? So all we need to do is convert our number of grams of ethanol into moles, and then just simply use our chemical reaction to determine how much heat is released. So as we begin this particular problem, we would start off with the 15.0 grams C2H5OH. We would divide that, 1 mole of the ethanol, molar mass was said to be 46.0 grams, and then form my chemical equation. I have 1 for the coefficient of ethanol, so I could say that 1 mole of ethanol combusting will be the equivalent of negative 555 kilojoules of heat being released. And then I can solve. So 15 divided by 46, that's going to be roughly around 1/3, and 1/3 of negative 555 would give me B, negative 181. So if we're solving for one of the other substances, say O2 in this particular case, I could use the conversion factor where I could say 555 kilojoules of heat are produced from the consumption of 3 moles of O2 instead. And I'd use that as my conversion down here in this part. So anytime you have a stoichiometry problem, think about the heat just being like a mole ratio with your coefficients for your other substances. So let's look at a second problem. Go ahead, pause the video, try to work it out and see how you do. But we'll go ahead and start up with this one here. And we have 5 grams of the peroxide, hydrogen peroxide. So we have H2O2. And it decomposes at a constant pressure. So I have a delta H again of negative 196. So that means that I can just simply write N plus heat over here. And as I begin my problem, we need to convert to moles. So I have 1 mole of the H2O2, and molar mass would be 34.02 grams of the H2O2. And then for the next part, we have our mole ratio with the heat involved. So I have the negative 196 kilojoules in the numerator. And notice now that I have a coefficient of 2. So I would now write 2 moles of H2O2. So 2 moles of H2O2 produces 196 kilojoules of heat. When we solve, we should end up with approximately negative 14.4 kilojoules of heat being released. Okay, so our second method is using the standard enthalpies of formation. So when we're looking at these, again, just a couple things I want to stress to you. Number one, when you see the little knot symbol, degree symbol up there, that means that you have standard conditions that are applying. So those standard conditions, for a gas, the pressure is exactly 1 atmosphere of pressure. For a solution, the concentration is exactly 1 molar, and the temperature would be 25 degrees Celsius. Those are the standard conditions that we would see. When we're talking about the standard states, that would be just what the normal state of matter would be for a particular element or compound at room temperature. So having N2 as a gas instead of as a liquid, we all know, you've probably seen liquid nitrogen. However, it will readily boil and vaporize at room temperature. So again, it's not a stable form of the element. So we're looking for the stable state of matter for a particular element at the room temperature. You'll be given a list of values for these different compounds that will form. A couple things for you to just kind of keep in mind, especially when we're talking about the element. The delta H for any element in its standard conditions is equal to 0. So that's the first thing. Now, the second part, because we're talking about the enthalpy of formation. So again, we're talking about the change in enthalpy that will accompany the formation of 1 mole of a compound from its elements. So we're always talking about the formation of the moles. So we're talking about making bonds in this process. So again, as an example, if I look at the formation of carbon dioxide, I'd have carbon as a solid plus O2 as a gas, and it would form CO2 as a gas, and the delta H would be listed on the table as negative 393.5 kilojoules per mole. Now, if we have a compound where we need to have different coefficients, fractional coefficients, that's okay, because we're always trying to form 1 mole of the compound. So if I gave you something like N2 plus H2 forming NH3. Now, in order to form just 1 mole of the NH3, I know you would normally have a coefficient of 2, I would put 1/2 for my N2. That would give me 1 atom of nitrogen. I'd have 3/2. 3/2 times 2 would give me 3 atoms of hydrogen, and that would produce 1 molecule of the ammonia. So if we did something like that, the delta H for the formation of ammonia is somewhere roughly around negative 46 kilojoules per mole. So I would see that listed on the table, but it's talking about the formation of 1 mole of the substance from its elements. So the main equation that we have for calculating enthalpy changes using Hess's law is this equation here. Delta H for the reaction is equal to the sum, that's the little sigma part right here, that's the sum of the enthalpy changes for the products multiplied by their coefficients. So that's the NP part here, that would be their coefficients, minus the sum of the enthalpies for the reactants multiplied by their coefficients, and then added together. So again, products minus reactants, think alphabetical order. P comes before R to help you with that. The elements in their standard states, again, are not included in the delta H for the reaction because their values in the standard state are 0. So let's now look at an example for how we can calculate the enthalpy of the reaction from the standard enthalpy of formation values. You'll notice here we're calculating delta H naught for the following reaction. 2Na as a solid plus 2H2O as a liquid forms 2NaOH aqueous and H2 gas. You'll notice in the data table you're given delta H of formation values for each substance. I have the 2 zeros for both of my elements, and then I have the 2 compounds. So again, I have delta H for the reaction equals delta H for my products minus delta H for the reactants. So I'm just going to make a quick little data table here. So I have delta H for my products. I have the 2NaOH. So I'm going to take their value, 2 times the negative 470. So that would equal negative 940. And then I have my delta H for the reactants, and I'm going to subtract these two. So I have 2 units of water as a liquid. Notice state of matter is important here because, again, physical processes, they're going to have different values, whether it's a solid, liquid, or a gas, based on the amount of energy that they possess internally to be in that state of matter. So in this case, I have 2 times the negative 286, and 2 times negative 286, what's that, negative 572. So at this point, I can take negative 940, subtract negative 572, and when we do that, we end up with 368 kilojoules of energy being released. So I would have a negative 386 kilojoules for my final answer for this. Now, College Board, they want you to put kilojoules per mole for the reaction as your unit for every single one of these problems. So even though I disagree with it, I'm going to go ahead and do it. So you have that negative 368 kilojoules per mole of reaction as your final answer. If you said a positive 368 kilojoules per mole, but you termed it as that enthalpy being released, that would be acceptable as well. So as long as you're somehow terming it as it being a emission of energy, you're okay. All right, so let's look at a problem from start to finish with you guys setting up an equation and solving for the standard enthalpy change. So when we look at this problem, we have to calculate the standard enthalpy change for the combustion of 1 mole. Again, key thing being 1 mole of benzene, C6H6, 2 CO2 and H2O. Remember, when we have the combustion, that means that we're reacting something with oxygen gas. So for this, because I have the 1 mole of benzene, I need to have my coefficient for the benzene just being 1. And I'm going to give myself plenty of space to write in the coefficients. So as I look at this problem here, I've got the 6 hydrogens versus 2. So I have a 3 here. And I have 6 for my number of CO2s, so I have a total of 15 oxygens, 12 for the carbon dioxide plus 3 for the water, so I need 7.5 for my moles of oxygen. So I now have my balanced equation in terms of 1 mole of benzene that's being produced, and so now I have my values on the table. So if I look here, I've got 6 times the negative 393.5. And if we look at that, we would have 2361, negative 2361, and then I have that plus 3 times the negative 285.8, and that would represent, I believe, negative 857.4. And so if I add those two together, that gives me a total of, what's that going to be? Negative 3,200 and, let's see, what's that, 18, I believe, 0.4. Okay, and then I have on the reactant side, I only have 1 times the 49.0. So I can set this up as my delta H of my products. So I'd have the negative 2361 plus the negative 857.4. And then I would subtract the delta H of the reactants, which is a positive 49, and so that should give me negative 3267.4 kilojoules of energy as my final answer. So now that we have just completed our jaunt through equilibrium, we can now focus on the characteristics of the enthalpy changes where we have our reversible processes. So please just remember, we've talked about this before with Le Chatelier's principle, but if the reaction is reversed, the sign of the delta H value is also reversed. The magnitude of delta H is directly proportional to the quantities of reactants and products in a chemical reaction. So if we have to change the coefficients in a balanced reaction, they're just going to be multiplied by some integer. The value of delta H will also be multiplied by that same integer. So for the Hess's law of summation, as we've talked about with kinetics, we have most of these reactions taking place in multiple steps. So Hess's law states that if a reaction is carried out in a series of steps, the delta H for the overall reaction will be equal to the sum of the enthalpy changes for the individual steps. So you can see here we have the CH4 plus the 2O2 forming CO2 and 2H2O as our overall reaction. But we can have some intermediate steps that are taking place within the process, CO plus 2H2O plus 1/2 O2 to get us to our final answer. So as we're looking at these types of chemical processes here, the sum of these steps, the -607 and the -283, would be equal to the overall change, which is represented by the delta H for 1 of 890 kilojoules. So for our next example, we need to calculate the delta H for the reaction. C is a solid plus H2O forms CO plus H2. So once again, we have a series of steps that together should equal the balanced equation for the reaction above. If we have to flip the direction of the reaction, i.e. make it a reverse direction, then in those situations, we would change the sign of delta H but keep the magnitude the same. If we have to multiply or divide by coefficients, we do the same for the delta H value. So when I look at this, the first thing I can tell you, which is helpful to do, is just simply underline the different parts of the reaction where we see it listed out in our overall chemical equation. So I have that, and where's my H2? There we go. So as we begin to look at this scenario here, my coefficients for the first substance, carbon as a solid, match, and I also have the same correct placement where they're both reactants. So as a result, I can leave the first reaction alone. When I look at my second reaction, however, if you notice, I have 2 for the coefficient here, but I have 1 for my coefficient in the overall balanced equation. There are no other COs to cancel off, so also notice the CO is a reactant in my sequence, but I need it to be a product. So not only am I going to flip the reaction, which I can designate as a -1, but then I'm also going to multiply it by 1/2. So overall, I'm going to multiply this entire reaction by 1/2, which means that I would take my delta H value and multiply that by -1/2 as well. So when I do that, that would now give me a positive, and what's that going to be? 283. And then for my last, I have the same situation. I have H2 with a coefficient of 1 in my balanced equation, but I have 2 for the coefficient here, and it's also on the wrong side. Same with water. I have 2 versus 1, and they need to be flipped. So I'm going to multiply this one by -1/2 as well. So when I do that, this one here, multiplying it by a -1/2, my delta H3 for that reaction should be 241.8 as a positive for the number of kilojoules. So I now have -393.5, positive 283, and positive 241 for my values. So just to make sure when we flip this, we have plenty of space here, so we can just kind of go back and look at what we've got. So I'm going to rewrite the first equation. C as a solid plus O2 gas forms CO2 as a gas. And again, everything else that is not part of the overall reaction should cancel out. So when I flip my reaction and I multiply it by 1/2, I would have CO2 as a gas breaks down into CO as a gas plus 1/2 O2 as a gas. And then for my last reaction, I have H2O, flipping that, multiplying by 1/2. So I have H2O as a gas, breaking down into H2 plus 1/2 O2. So you'll now notice I have a CO2 as a reactant, CO2 as a product, both with coefficients of 1, so they cancel out just like the like terms that you would see in a multi-equation system. For your math, we can cancel out the like terms here. I have one O2 molecule as a reactant. I have half plus another half as products, so they too would equal 1 and would cancel each other out. And then you'll notice all that I'm left with, carbon plus water, forms carbon monoxide and hydrogen gas. So we have everything balancing out from a stoichiometry standpoint, and now all we have to do is add our numbers together to figure this out. So negative 393.5 and 283, that'll be negative 110. Negative 110 plus the 241 should give me 131.3. So C would be my correct answer. All right, so now it's your turn. Go ahead and try to pause the video and solve this problem. Calculate delta H for the reaction. NO gas plus O yields NO2 gas, given the following information. NO plus O3 yields NO2 plus O2. 2O3 forms 3O2, and O2 forms 2 atoms of oxygen. You have the delta H values given for each individual reaction. Pause the video and try to solve the problem. All right, so as we look at our answers, again, the first thing that we need to do is identify where in our overall reaction each of our different components are and what their coefficients are. So if you notice, both the NO and the NO2 are found in the first equation only, and they are both found in the correct positions with the correct coefficients. So I have to do nothing at all to my first reaction. Now, when we get to the next part, the only other part of the overall equation is the oxygen atom. So I'm going to move down to the third reaction instead of starting with the second. So notice here that I have 2 atoms of oxygen, and each one of them is a product versus the need for it to be a reactant. So I'm going to flip my reaction, and I'm also going to multiply by 1/2. So I'm going to multiply this by a negative 1/2. And when I do that, I end up with a value of negative, I believe that's 247.5. And so now by flipping that, I now have the O2 as a product, whereas in my other reaction, I have O2 as a product as well, so I need to flip it. I also have O3 as a reactant on each one, so I'm going to flip the second reaction, and I'm also going to multiply by 1/2 again. So when I do that, multiplying by a negative 1/2, that will give me a positive, what's that, 71.65? No, 71.15. Excuse me, 71.15. And so now at this point I'm ready to solve, but let's go ahead and rearrange our equations just to make sure that we have everything cancel out and have the stoichiometry match. So I would have now 3/2 O2 going to O3, and finally O going to 1/2 O2. So again, only the NO and the NO2 can stay. I have an O3 as a reactant and O3 as a product, so each of those would cancel. I have a total of 1/2 O2s plus 1 O2, so there's 3/2 O2 as products, and one of them 3/2 O2 as a reactant, so the sum will add up and cancel off. And if you notice, all I'm left with 1 NO, 1 O, and 1 NO2. So we've done all of our rearrangements correctly. So now if we take our values here and add them together, we should come up with an answer of negative, what's that, 375.25 kilojoules. All right, so let's look at one more example for the Hess's law of summation before we move on. And we have NH3 forming 1/2 N2 plus 3/2 H2, delta H of 46 kilojoules, 2H2 plus O2 forming 2H2O as a gas, being negative 484 kilojoules. And we want the overall reaction, 2N2 plus 6H2O forms 3O2 and 4NH3. So if you notice here, I have N2 as a reactant in the main equation. I have it as a product in our sequence. I have H2O as a reactant, H2O as a gas, as a product in the sequence. 3 O2 gases. I have O2 gas, one's a product, one's a reactant, and then the 4 NH3 versus 1 NH3, again opposite sides, so I need to flip the direction. So I'm going to take this reaction and multiply it by a negative 4. So that means that my new value for delta H, when I multiply it by a negative 4, would be negative 184. And when I look at my second reaction, I need O2 to become 3 for the coefficient and water to become 6. So I need to multiply my bottom by a negative 3. When I multiply that by a negative 3, that becomes a positive 1452. And now when I add those two together, I get a positive 1268. Final answer. So the last one that we're going to look at is dealing with bond enthalpies. So when we look at bond enthalpies, we are breaking apart compounds rather than putting them together. So this always is an endothermic process. If you remember, bond breaking is always endothermic, bond forming is always exothermic. But again, we're looking at the sum difference between the two. So when we look at the average bond enthalpies, we have a set of values for the different atoms that are bonded together. Please understand this is not quite as accurate as the standard heats of formation, because this is an average of all the different types of compounds that are present for a particular type of bond between two atoms. So they're taking the composite of all the different compounds, giving that average bond enthalpy. So it's not quite as accurate, but it will give us a good rough estimate, typically within 10% of what the actual value should be. So you have a table here that's given. I don't know why it's a little messed up with the font there. I couldn't figure out which font it used to have just the normal symbols. So I placed another table in on the next page that will help you as we work through a couple of example problems. So as you're looking at this, this is where Lewis structures are going to come into play. So you need to get back into your brain how you can use your Lewis structures to figure all that information out. Okay, so for our first example, we have the calculation of delta H for the combustion of ethane, C2H6. We have the Lewis structures given to us, which gives us two C2H6s plus 7 O2s, forming 4 CO2s and 6 H2Os. So for your bond enthalpy calculations, we have a formula that we use, which is delta H for the reaction is equal to the delta H for the bonds broken minus delta H for the bonds formed. So just like I have mentioned to you guys when we did the standard heat of formation, think about this if you're worried about forgetting the sequence, always go in alphabetical order. Products minus reactants, P comes before R. For the bond enthalpies, bonds broken minus bonds formed. Again, B comes before F alphabetically, so you can remember that. In this, the bonds broken, this will be our reactants. The bonds formed, that would be our products. So the difference here is that when we talk about the standard heat of formation, that is referencing the formation of a compound from its elements. Here we're talking about breaking the bonds back from a compound into its elements. So that's why it's in reverse. So in this case, all I need to do is set up a little data table. So I have my delta H for my bonds that are broken. So I have from this compound here, if you notice, I have 1, 2, 3, 4, 5, 6, but I have 2 molecules, so I have 12 CH bonds. And if I look at my data table, first one on the list, conveniently, 413. So I have 12 times 413. So that would be 4956. And then I also have two C single bonds, which is actually next on the list conveniently. So I have 2 times 348, and that should equal 696 if I'm doing my math right. And then finally I have 7 oxygen-oxygen double bonds, each one being 495. So that one is right over here. So 7 times 495, that one should be easy. 500 would be times 7 will be 3,500. So I can subtract 35 from that, and I have 3465. So at this point, I can now add all these together, and my delta H for the bonds broken in this case, we have 4956 and 696. That would be 5652. And then we add 3465. So 56 and 34 would be 9,000. 52 and 65, that would be 117. So we have 9,117 kilojoules for my delta H for the bonds broken. And now we can do the same thing for the delta H of the bonds that are formed. So I have 4 times, I have 8 because I have 2 molecules, or 2 bonds per molecule. So I have 8 CO double bonds. So that will be 8 times the 799. And so that value would be 6392. And then I have 12 OH bonds. So 12 times the OH, 463. And when we do that, that one, of course, is not quite as easy. Let's see, 12 times 400. So that would be 48, 792. 463 times 12, or no, 756. So that would be 55, 56, I think. So if we add those two together, that gives us an 8, a 4, a 9, 1, 1. I think that's right. Hopefully. So I have 11,948. So I would just simply take for the delta H for the overall reaction. Sorry, I should have worked this one out first. I have 9117 for my kilojoules, subtracting 11,948. And that one I should be able to do in my head. I'm going to do a negative 28 and then 31. So negative 2,831 kilojoules. All right, so I almost kept it under 30 minutes, really close. So we got one last problem. We have H2 plus F2 forms 2HF. So this one should be pretty easy. If you notice, for that balanced equation, I have just one H molecule. So I have 432. I have the FF, so these would be my bonds that are broken right here. So I can add those two together, and that would give me 586 for my kilojoules. And then I have the HF bond as 565. This would be my bonds that would be formed, but I have 2 of them, so I need to multiply that by 2. So that would give me positive 1130. And so now products minus, or reactants minus the products, 586 minus the 1130. And when we do that, we have, what's that, 56 and 5. So negative 556 would be my answer in kilojoules. Okay. So that wraps up the different methods for calculating delta H for the basic type of problems. We have one other method that we will use when we get into the next video again, which will be talking about Gibbs free energy to calculate it. But for now, you guys can go ahead and start working on the practice problems that are on Teams and come to class with questions tomorrow. Have a great day.